right, good morning. Welcome back to Data Structures. I'm sure all of y'all are thoroughly enjoying Project 1.
Sure.
Yeah.
If you want to call it that.
Oh, it's a good old time.
Nightmare number 1?
Nightmare number 1. So today...
It's okay, he's assigning nightmare number 2.
Oh no, he already did.
Yeah, you saw it up.
We're
Actually, I'm actually going to enjoy this one.
Yeah, this Project 2, if you thought Project 1 was tough, yeah, I get it. Project 2 should probably be one of the easier projects out there, hopefully. If not, come talk to me. But today, yeah, we'll go over Project 2, but first we need to start heading into searching and sorting algorithms. Part of data structure is just basic search and sorting. We'll go through that. Hopefully in the lab, we might actually be able to, if we have time and everyone's fast, we might be able to do the lab in class, which I'm sure all of y'all would appreciate, or at least the first part of the lab. And then we'll go over your Project 2.
Nope, we're working on the project.
By the way, Project 2, all of Project 2 can be done, everything leading up to this point, so you do not need what we're talking about today to do Project 2.
Awesome.
All right, I really don't like that. Okay, those beginning slides are a little
Are you
frustrating.
covering quicksort too?
Am I doing what?
Quicksort?
Quicksort? Not today,
It is too hot with this.
but we will go over quicksort and merge sort and heap sort. And if y'all really are adventurous, we'll do some other sorts as well, radius sort. But yeah, we're going to do bubble sort, selection sort, insertion sort. Yeah, bubble sorts today.
We have bubbles.
Bubble sorts today. Next will come selection and insertion.
I think she actually meant real bubbles, not
Oh, no, these are computer bubbles. You just have to use your imagination. It's like bubbles.
The more you know.
All right. So, why is searching important? Why is searching important?
So you can find things.
You can find things. All right, great.
You asked.
Look,
Very vague.
We're done.
A vague response.
so you can have ordered linked list and an order array. I will stick with the order array today. The key is the member that identifies the data set. Wow, haven't we just gone through all this? Key comparison, comparing the key of the search item with the key of an item in the list. So you can count the number of key comparisons. All right. That sounds a little confusing. But let's think of sequential search, linear search, which ends up being the same for both arrays and a linked list. Start at the first element and examine each element until a match is found. So what is the complexity of linear search?
Oh, it's the
wow.
end.
Oh, man.
Oh,
And I meant to say that. I really did.
drink more coffee.
And eat.
And eat.
I can't drink coffee.
Yes, Malik?
I'm just actually really go get some coffee.
Yes.
Wait, how do you say coffee? Coffee.
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 It's okay. I've been
All right,
working
so,
on
yeah, we've already...
That New York accent.
All right, statements. Do we? Okay, I guess, forget these slides.
No,
Just jump into the code.
please.
Searching.
I like the fact that my name is there.
Yeah, yours is up there.
Yeah,
All right, so
Carla's, I believe.
let's go gvim
You will forever
linear
be in the
search.cpp.
repository. Goals.
You wish you would.
So we'll include iostream, int main, int argc, char star argv.
Honestly, like,
What's that?
In like 10 years, we push code to your repository.
All right, nice and big. Can everyone see in the back? Or would you like to turn off the lights so everyone falls asleep?
But here, I finally
No,
used the
please don't
lab.
turn off the lights.
All right, we're not turning off the lights.
Aw.
I refuse.
Can you see?
Yeah, I can see fine.
Good.
I got 20/20
They're like,
just
here, I
like
finally fixed your lab.
All right.
I use a little bit at that point.
So let's see, I think it's manned srand.
What?
Good. So if we want to get some random numbers, how'd y'all do random numbers in the other class?
Fine.
Is it math.random?
Oh. In C++, I don't remember.
You don't remember? Okay, good.
I
So
don't
we're going
remember anything.
So we're going to-
Ram.
seed the RAM with 100. That way we will always generate the same random numbers. Yes, I just said that. We will always generate the same random numbers.
S-read?
SREAD, seed randomization. See, look, jump over here.
Why wouldn't it be like the R in front? Why is it? I don't like that.
No, why wouldn't it be
and then rand.
Why you put the R in the middle? That doesn't make sense.
All right. Well then, we'll go ahead and create. Let's see, a good old enter. Let's see. What should we call this?
Numbers.
No, sure. Equals new, and how many should we have?
25.
2025. Let's go ahead and make this a little define up here. Size as 2025. That way we can just type in the word size whenever we want that number, and if we decide to increase the size, we can do that later. Good. So for int I equals 0, I is less than size, I plus plus, and then we can just print out, or we can set numbers sub I equal to rand, and if I remember everything correctly, this will actually generate random numbers. Let me go ahead and comment my code. Let's see the random number generator. Create the number.
I'm kind of jumping the gun here, Dr. West. But what's the runtime for bubble sort?
We'll get to it.
Okay.
Put random numbers into the array. All right. So I'm going to create a little function up here called void print array, passing in numbers. That way, if we ever want to print, we can just do for int I equals 0, I is less than size, I plus plus, and then we can see out numbers sub I, and then put a little comma space afterwards. And then when we're done, we'll put out a new line. That way, it all prints out. So let's see if we did this correctly. What do you think? Do you think it'll compile?
Yes.
Oh,
Ha! I win.
S read is not.
oh, because it's not sread, it's srand.
See,
Oh.
it didn't make sense.
Oh, we were so close.
We pointed
Where's
that
Chris
out
when you
though.
need
We
us?
were like,
That's
why is
gotta
it
be
SRE'd? Like, why would we seed with an R in the middle of it?
Right. Now I understand what you were saying.
Yeah.
So if I an a dot out,
We win.
so nothing happens, probably because I never told it to actually print the array. Good morning.
Yay, someone else is here.
Our class is dwindling.
All right, so I can print out, look at all those numbers. And if I run it
There's
again,
a lot of numbers.
see, it's the same
that?
random number every time.
What, that's the same random number?
Yeah, it's the same random numbers.
Oh. I meant like it's the exact same number.
I was
every
about to say,
time. I
no,
was
it
like,
is
they're
not.
not repeating. They're not.
The same random set of numbers because we always seed from 100. All right.
Yeah.
So how do we do a linear search? Let's see. Void linear search.
Can we like
Int.
define it so the numbers aren't so large?
So the numbers aren't so.
Large.
Oh.
Okay, we could do that.
So they're not like 10 characters long?
Sure. Define max. Max.
Like,
No, that would be the link. So max. Max int size. What do you want it to be?
like 5 letters? Numbers?
Just 5 numbers. Okay. All right.
Yeah.
That works.
Okay. So then we'll go numbers ram mod max int size.
Wouldn't that make it?
So there, that's what you want. Everything, all the numbers are now less than 10,000, right?
That works for me.
Well, I think we were saying like you could go up to 5 digits, so you could if you wanted to do that. We don't.
Oh,
have to
5
change
digits,
this
sure.
out. We don't have
No,
to
no, no,
change
no.
it,
You
but
see,
I wanted to
the whole
ask
point of
if-
doing these defines is just add a 0 right there. You go
Okay.
back, and now we're done.
I was about to say, couldn't you just do like 99,999? Do that?
Well, since
or-
you're modding it, it's at 10,000 or 100,000, never actually going to happen because you're modding it. If that number was
Okay.
10,000, mod 10,000 is
0.
goose egg. Yeah, 0.
Use it.
Goose egg. 0. All right, here we go.
That's what 0 is now.
Yep, it is a goose egg. Okay, so if we want to do,
These are nasty creatures.
Why did it have to be a goose egg?
I'm going to do index of int. Yeah, why did they come up with that?
Like, why goose?
and then int.
Like,
Geese are mean.
it's so random.
So returns the index of key.
But there's so
Okay.
many creatures that actually lay eggs.
Platypus.
I'll do
Yes.
linear index of. So this is a linear search. This is a linear search. All right. So how do we do a linear search?
Just go through the array.
All right. So we're going to go through the array. For int I equals 0, I is less than size, I plus plus. All right. We're going through the array. Then what do we do?
Find key.
How do we find the key? If
The number of the index equals the key. Return something.
return I, because we're trying to return the index. And if all else fails, we return -1.
Sure.
Sure.
I think
All right.
that's how you respond a lot, too.
That's true.
We're picking it up. Be careful what you teach us.
All right, so C out. Let's see. Location of what number do you want to search for?
25.
25 is
2,965.
well. Then we got to do the linear index of passing in numbers and 25, right?
I like your treasure. Thank you.
Wait, number or numbers?
Numbers.
Numbers.
Let's see if it'll work. Oh, I misspelled something.
You forgot an S on the end.
Sure did.
Sure did.
Location of 25 is -1. That means it's not in the list. Let's go find something that is in the list, like that number right there.
Like that one.
That one right there.
Right.
Right there.
Right there.
61645. Boom.
This is like that whole, like the air,
Hey, location is. There we go.
the Apple Air whatever thing, where it's just like it generates a random code when you want to hook up your iPad and stuff. In my calc class when we had Greaves, we used to he'd be like, I'll give you like 1 extra credit point if you get it right.
Only
It's like a
one?
4-digit code, yeah. Dude,
Dr.
he
West.
never gives
Yes.
extra credit.
So
Like, you have to
I was
earn
working at
so
the
many
Charleston
different
STEM
points.
Festival. I dressed up as Bucky, but guess who dressed up as the Charleston
Good job.
grad?
Good job.
Oh, yeah, that was Greaves. That was Greaves. All right.
That was actually really funny to see.
So back to the code, so we can actually get work done, so you won't be crying tonight when you're trying to work on your lab and your
Oh,
projects.
still crying, but it's okay.
No, okay, I'm sorry.
On the inside.
Well, anyways,
Well,
On the outside. What are you
so
talking
what?
about?
I see no tears.
Oh.
don't forget, I have a test today in scripting.
All right.
Yeah, I know. I
So-
get to study.
My goodness.
You're killing us.
So what's the big O of our good old linear search?
Not a good
Oh,
one.
then.
O of N. Why is it O of N? Sydney.
What? I just said not a good one. She answered with the real answer. Because it has to, I guess it has to search through everything in a straight line, and instead of just getting it.
Right.
So
So
it takes too much time.
we assume N is the size.
Yes.
On average, how far along the list is it going to take to find something?
A while.
Halfway through. So 0.5 of N, which is O of N.
Yeah.
Following, Malik?
I'm pretty sure.
Okay.
Sure.
He's like
All right.
drinking coffee. Hold on.
So let's see. Sequential search.
It's not coffee, it's coffee.
The
A word is a word.
the statements before the for loop and after the for loop are minimal, so there's not much load up time here. Statements of for loop repeat several times. Speed of the computer does not affect the number of key comparisons required. Do you understand that?
Nope.
Even if we made just John was like, nope.
Yeah, you're about to cry.
Not at all. Whatever you just said
I
did
was
not.
crying.
It did not
there's
work.
words on the screen, but I'm just.
It
it's
did
just-
not work.
Woo!
All right. So if we had the processor inside of an old NES or a modern supercomputer, and we ran this code, would they both have to compare numbers of sub I versus key the same number of times?
Yes.
Yes, just one would do it faster than the other. Okay? That's all we're
NES
saying.
would probably do it best.
Whew.
NES is
All right.
the best.
When you take architecture, we'll have to help you out
Go
there
NES
soon.
or go home.
All right. So another analysis. We already did this once, but let's do it again.
Do it on a calculator.
So if L is a list of linked n, guys, seriously,
I saw a meme this week and it's like, oh, you can play Doom on a calculator. I was like, what?
if it's not in the list, how many comparisons? If n, the key, is not in the list, how many comparisons are there?
All of them.
All of them, which is how many? N. N comparisons. Great.
Correct.
So, but if the item is in the list, if it's the first element of the list, it's 1. That's the best case. If it's the last element of the list, there's in comparison, so that's the worst case. So the average is what again? Essentially 0.5, or n plus 1 over 2, because you do have to compare that middle one, so there's that plus 1. All right, binary search can be applied to sorted lists. All right. Oh yeah, if there was list, how could we do this faster if the list was sorted?
Couldn't you go like halfway and then go halfway again? And
So we go halfway, and then what do we do?
just check on either side if the values on either side are higher or lower than the one that you have. And then you go halfway again.
Did y'all learn that in Intro to C++?
Yeah, I remember. I think so because it was just
We
kind of
talked
like
about it last semester.
you go halfway if it was in there, or if you
That's
need to
awesome.
go more, you just go to the next half.
Right. So if we have
Yeah, we
Keep
actually
cutting it in
learned
half.
something.
we learned something. All right. So 0, 4, 24, and
36.
Okay, 36.
That's a B6.
That's-
We're not playing bingo.
133.
I was thinking more like bingo.
I thought battleship automatically.
Wow, I feel like an old person. Why was my first instinct bingo?
So if we were trying to find 256, we'd start at the 36, and what would we say?
It's higher.
Higher,
So you go to
so-
the other, so you go 256.
So we go over here. So since it's higher than 356, we now, or 36, sorry, we now know we just need to search the upper array, which happens to be this. Which means we've cut off half the array, right?
Yay.
And then we go to the middle. Oh, well, we found it, so that was pretty
It's been
quick.
chopped.
All right. We'll go through this again. So compare an item to the middle. If the search item is less than the middle, only search again on the lowest. If the search item is in the higher, search in the upper half of the list. All right. Oh, good. We get a little picture here.
Pictures?
Oh, pictures.
I love pictures.
They never give us pictures.
I just drew on the board.
No, they do.
Oh.
You too.
No, they give us
He
pictures.
draws on the board
for,
every day.
They give us pictures for one thing, but not for the other.
All right, so if we were just, length was 12, we'd start at the mid of 39. All we're saying is the mid is 39. Everyone good with that?
Yep.
Great. So if we're trying to search for 75, we compare against 39, we notice, oh wait, it's higher, so we can search on the upper half. Okay. Wow, so it stops there. Thanks, guys. So then we'd either go to the 66 or the 75, probably go to the 66, and would it be higher or lower? Higher. So then we have 75, 89, 95. We go to 89, is it higher or lower?
Lower.
So then we jump to 75 and we'd be done.
When we did this in C++, I think we created a game. Like, pretty sure. And that's how we tested this.
Yeah, I think I know.
So what is the big O of this? O of 1?
Log in.
Log in. Why is it log in? I forget.
Because you checked
It's like the opposite of exponential.
It's the opposite of exponential,
It's being
okay.
halved every time.
Because what, sorry?
It's getting halved every time.
It's being halved every time. That's the intuition. If you're halving something every time, then it's usually a log base 2 of n. Okay?
Oh, no.
Okay.
Isn't that slower?
No, log base.
Then linear? Log base 2 of n versus O of n? No. Log of log of n is way better. I mean, log of n is way better than just n.
What?
All right, let's look at it this way. So if the list has 1,024 items, that's 2 to the 10th items, it would require at most 11 iterations to find x.
Okay.
Not bad.
In this case, at most 22 key comparisons, because when you're doing less than, you actually have to do 2. You okay there? You okay? Sequential search requires 512 key comparisons if x is to find x and L. All right, what if it was 1,000,000? How many iterations would you need?
500,000 at least.
For linear, how about for binary?
You like 40.
40? Close, lower though.
30.
Oh, key comparisons. Key comparisons, yes.
22.
Key comparisons, you require about 44 iterations, so it would require 21. Or 42, I'm sorry, iterations.
Now my numbers are almost up.
Oh.
All right. So it's how do we write binary search if we can't sort yet?
Good question.
All right, we're going to skip over to sorting because that's just silly. Oh, wow. Look at those pictures. All right, back over to sorting. Sorting algorithms. So compare the performance of commonly used sorting algorithms. All right, that's great. And we're going to use array-based right now. We're going to stick with the basics. The good old bubble sort. Suppose you have a list of items indexed from 0 to n minus 1. It's a series of iterations. Compare successive elements. You know, list of index and index plus 1. If the first one is greater than the other one, then swap them.
Shaking our rings off, it's getting serious.
The gloves have come off. All right, so for example, if this was your unsorted list, and I guess they're going to do it this way, where they want the lowest on top and the greatest on the beginning, you compare 10 and 7. 10 and 7 are 10's bigger than 7, so you swap them. You compare 10 and 19. 10's not bigger than 19, so you leave it alone. Compare 10 and 5. 19's bigger, so you swap them. And then you compare 19 and 16. 19's bigger, so you swap them. Okay? So what you think of, the way that why it's called bubble, is the largest number has bubbled up to the top. Or in this case, the bottom, which is backwards, but whatever.
Yeah, why would
That's
you?
some bubble.
Yeah, it's a reverse bubble. Well, I just need to take
Bubbles
my
go
computer.
up, heavy things go down.
Okay, these slides are terrible, I know.
So basically,
They're heavy
Draw
bubbles.
pictures.
it's a reverse bubble.
All right.
Pictures with
The
the
air is heavier
Hey.
than the liquid.
All right, here we go. So we compare again 7 and 10. No need to change. Compare 10 and 5. We do need to change because 10 is bigger than 5. It gets swapped. Notice last time the 10 stayed where it was. Then you compare 10 and 16. Nothing needs to swap. So now the second largest number has bubbled up to the top. What do you think happens next?
We do it again.
We do it again.
Yes!
Compare 7 and 5. 7's bigger, so we swap it. Compare 7 and 10. 10's still bigger, so we don't swap it. Now the third number has bubbled up to the top. And then finally we compare the last two. They're okay, and now we've sorted the list. All right?
Do you know how many times you have to do it for your post?
How many times do we have to do it?
Like how would you know
Please stop.
the amount of times you'd have to do it? So like when you're coding it.
Right. So let's take this one step at a time. Let's jump back here. What about just this top iteration? What'd they do?
Sorted through it once.
So we went through it once. All right. Let me go over and get this prepared. Let's go void bubble sort int number. Ooh, that was bad. Star numbers. All right. So they're going through the list because it looks like they're comparing. Notice they compare all the way down. All right, let's do that. So let's go for int I equals 0. I is less than size. I plus plus. All right, and then you have number sub I. Well, let's see what we can do here. So where are they comparing? They're comparing
The numbers.
I equals 0 and I equals 1
I0 and I.
is 1.
Right, so they're comparing I and I plus 1, right?
Yes.
All right.
That word.
And what are they comparing them? Which is
Greater.
greater. All right, so let's do that comparison first. If number sub I is greater than number sub I plus 1. Actually, before we do this, we have a memory problem already. What is it?
Segmentation fault.
Right. Why is there a seg fault?
Because they're
I plus 1 is eventually going to go out in size.
Correct. So how do we fix that?
Size minus 1.
There we go. Boom. All right. There. Now that the memory error has been fixed. What?
It's a cool bean.
It's just like the person at Wendy's the other day was like, awesome.
All right. Cool beans, cool numbers.
I guess.
All right. So if number sub I is greater than number sub I plus 1, what do we need to do?
Nothing.
Swap.
Swap 'em.
Swap. We're going to say,
yeah.
we want to swap. So how do we swap? Oh, this is a great question.
don't you create like a temporary variable?
Okay, we'll do it. Yeah, so you can create a temporary variable. All right, then what do we do? Oh, I set it equal to the first number. There, I give you the first hint. Now, what's the second step?
Set numbers to, or numbers plus 1 to
No.
numbers.
No. Set number to numbers at I to numbers at I plus 1.
Because you're saving what that value is.
Yeah, and then you say numbers I plus 1 to numbers at I. Or no.
Temp.
Yeah.
There we go. Okay, great. So, all right. So, bubble up the topmost number. All right, great. So that's what that's doing. So that's one iteration of bubbling up the topmost number. How many more iterations do we need?
A couple. Depending on.
It depends.
In this one, 2 more.
Hold on. We had 1, 2, 3, 4. So there are 4 iterations.
Oh.
And the size of the array is 5. What do you think?
So you would do it the size of the array?
Yes. So we need to do this the size of the array number of times. All right, so I'll do another for loop. For int j equals 0, j is less than size, j plus plus. All right, are we done? Might actually be done.
What?
Well, you need an else.
All right, let's see what that does. Let's see. Bubble sort of numbers. Oh, I mistyped something. Oh, line 33. No, I didn't. I just forgot to put my S.
We do that a lot.
Hey.
It's a lot of numbers.
Hey, but are they in...
They're going in order.
They're in order. Does it
Hey.
start up here?
They're not.
Hey, it works.
Well, I like the fact that it shifts.
Yeah, you like the
Down.
shifting?
That's me.
All right, so...
Sorry.
Is there any optimization we can do?
What if,
You can do it recursively.
well,
How would that optimize?
Fair enough.
Craig. Think, then speak.
What's my name again? But with recursion, it's calling itself again and again. That way, there's less lines of code, so it could be optimized in that sense.
That doesn't necessarily mean it's faster. There's a lot of algorithms that are far more complex than this
Optimizing is-
that are faster.
First, user group time.
so what if it was sorted before it ran all those times?
Okay. Let's step back. When I'm done with one iteration, what has happened? When I'm done with the first iteration, what has been accomplished? There we go.
The largest numbers at the end,
The largest numbers at the end. When I'm done with my second iteration, what have I accomplished?
second largest numbers at the second
Right.
end.
So do I need to go and compare those again?
No.
No. So I don't need to go necessarily to size minus 1 minus j.
I like that.
Got it.
Because at first j is 0, so you go all the way to the end. When j becomes 1, you go all the way, minus 1 or minus 2 in this case.
Oh, J.
When j is 2, et cetera, et cetera. So it's at least shrinking how many times we have to run through it. So let's go ahead and run it and make sure it's actually doing it correctly and I didn't mistype something. It's looking pretty good. Looks good.
Look at all the pretty numbers.
Pretty numbers. Okay. What is the complexity of this algorithm?
O of n squared.
O of n squared. Why is it n squared?
Because there's two for loops.
It's 2 for loops that are both based on size, which is n. So it's essentially 2 for loops. But wait, I'm subtracting by j.
Oh, wait, there's more.
Why does subtracting by j not mean anything here?
But you're still doing two
Because it's
for
still
loops.
n squared.
Right, well why is it still n squared? Why is it subtracted by j? So obviously the outer loop is O of n, right?
Well, it's like if it was just like
Still doing it,
n
that's
minus
fine.
j times n, you're still gonna get an n squared out of that. And isn't it like the highest power is the
O
only
of-
thing that matters?
What is it? The highest power. Well, hold on. The first time you execute this, it's what? Size minus 1, we'll just say n. N minus 1, then n minus 2, then n minus 3, n minus 4, n minus 5, all the way down. So on average, how long is that for loop? How many times does it execute? Yeah, about 0.5 times n, which is still n, right.
You may have taken out sometime, but you didn't completely take out. No, I don't like that. Why did you do a capital letter?
Oh, I'm so sorry. Okay. So how many comparisons? It's how many in big O notation? How many comparisons are it? I'm just making sure this is clear. How many comparisons do we do in big O? I'm sorry. What's the complexity of the number of comparisons?
That's right.
N squared. What's the number of swaps we do?
Halfway.
Don't know.
I didn't count.
What would be the worst case?
The whole thing.
You'd have to do it every single time, which would be n squared, right? What would be the best case?
Once.
Well, you never have to swap. They're already sorted, right?
So 0.
So that would be O of 1. Right. O of 1. I'm sorry. You're right. But, yeah.
That would be lucky.
All right. So total number of comparisons, about n squared. Number of assignments. Well, worst case, still n squared, like we said. Wow, it's not going to do anything else? Okay, great.
Good job. Bubbles.
Oh, okay. So that's all the sorts we're going to do. So let's jump back to selection sort. Binary search. Whew. All right. So now that we have something that is sorted, we want to do our good old divide and conquer, where we talked about we have our giant array. We jump to the middle, and we go up or lower, and we basically zero in on the array. Okay. Do I need to go over binary search again? But basically, you want to find something. You first compare the bid. If it's equal to it, you're done. Otherwise, you need to search the higher or the lower end, and you keep repeating this until you're done.
You could show us how to code it.
Right. We are going to code that now. So let's see. We got bubble sort. We'll do int binary. Oops. Binary index of. We passed a bunch of numbers and the key. All right. How do you want to do this?
Easy way.
Okay.
You do size divided by 2.
What's that?
Size divided by 2.
All right. So we'll create. Okay. You want to find the mid. So we have int mid equals size divided by 2. All right.
What if your size is odd?
And it'll round up. I mean, if
It'll be,
you
yeah, it'll be
round up,
truncated.
right?
Yeah, okay.
Now, you want truncated or do you want to round? No, we'll find out later. We'll think about it later. So we have the mid. Now what do we do?
We
to, not to the mid, but if key equals number sub mid.
Yeah.
Right. And if it is, what do we return?
Then return mid.
Mid, right, because we're returning the index of. Okay?
Okay.
Now if it's not, what do we do?
Then we need to see if
to the
it's
next
less than
middle.
or greater than.
Okay.
I'm assuming it's word, right?
Yeah, so if key is less than number sub mid, else we want to do something else. All right. So what do we do if it's less than?
You go to the middle of the less than.
Go to the middle of the less than. All right. So we want to
Divide mid by 2
Divide
again.
mid by 2.
divide. Okay.
I don't know. It's
Mid divide equal. Sure, sure.
We're not doing this the way you want.
What game?
All right.
Do you
Mid.
see why now we're having so much problems?
We overcomplicate everything.
No, it's fine. It's fine. So mid divide equal to. Now what do we do?
See if that equals it.
Okay.
Another if statement.
All right.
Necessary.
No, hold on.
If key equals number sub mid, we what do we do?
Return.
This needs to be like in some sort of loop or something.
Right. This should be in some sort of loop because we're just repeating the code we just had up
Because
there.
we're about to have a lot of. Eventually, you can't see it.
Yeah. Eventually, it would. Yeah, it'd be terrible.
It would be. It's gonna be.
So yeah, what do you want to do? Loop, or do you want to do something else, Craig?
No way
I
you
say we
said
pull,
his name.
pull a Craig and we do some recursion.
Oh
What's
my
that?
God.
Recursion.
You want to do it recursively? That's great. I like that idea.
You actually do?
Huh?
Yeah, recursion's awesome.
Yeah. It's awesome.
I wasn't being completely. I don't know what the word I'm looking for is.
Facetious.
Facetious when I said Craig. All right.
You just love messing with me.
Yes. Well, I mean, when you start getting trolled, you have to troll the troller. All right, binary search.
Okay.
All right, so if we're going to do this recursively.
We need a base case.
Okay.
Oh, I forgot about base cases.
Oh, I don't know.
Dr. West,
Yes.
I know
I'm sending you a YouTube channel where
Me too.
Hungarian dancers actually do like the algorithms that we're covering right now.
That's great.
Hungarian answers.
Yeah, there's a lot of funny things that do these algorithms. All right.
I'm not kidding.
So index of, hold on, and this is going to be a recursive one. So we're going to be past numbers, and then key, and then we need to be past something else. Which what?
Oh, yeah.
You misspelled. It has to be numbers. Actually, it's just numbers.
All right, hold on. So we want to recurse in this case, right? All right. So if we're going to recurse, we'll go binary index of. We'll pass again numbers, the key.
Numbers, not numbers.
Numbers. S.
Otherwise, it's going to be broken.
Totally broken. All right.
Break it,
I better put a. I'll,
Travis.
I can't remember what the third thing is.
what has happened? Why are we like this? Yes.
You
Maybe
said
it's
broken.
because you pulled a Craig.
Holy Craig.
Well, you
Hey,
said.
what? I don't remember what's the third thing
You
that you
said
have to say.
All right. If we're doing this recursively, and we've just specified that what's here? Key is less than. What does that mean?
Oh, wait. You want to pass it to mid?
Okay, so we got to pass it the mid. You're on the right track. I'm going to help everyone along, and I'm going to pass in the start and the end.
The end.
Okay.
Okay.
What?
We're going to.
Oh, I guess mid would-
That's what I'm talking about.
Oh no.
All right. So in other words, this binary search, as I say, we have these numbers, we have this key, we have a start and an end. You need to search between that start and that end.
So for if it was greater than, then you'd send it mid and then size minus.
Right.
1.
Okay. So hang on. It's recursion. So the first thing we need to do is
Base case.
base case, which is
If it equals the mid?
and there was like
well, if start is greater than end, we have a problem, right? Okay. Otherwise, we'll go ahead and compute. We'll go ahead and compute mid up here.
What if start's negative?
End minus start.
What if start's
What if
negative?
starts negative?
Can you test for that too?
Start.
And what if end is negative?
Yeah, what if somebody passes a negative start? Or a negative
Okay.
Well, no, negative.
No, that won't happen. Divide by 2.
Okay.
I
So-
mean,
What?
Just covering all my bases.
Okay.
that's what we've learned to do.
So,
But really.
so really,
All the as my old physics professor said, don't shotgun it.
so right now, let's just say that start is 0, and then end is size. Well, actually, we're taking care of that one down there. So it's size divided by 2.
Do you want to switch screens?
You might
No.
want to switch screens. Online people's can't.
Online people, I just wrote 0 and size divided by 2 on the board. All right, so we have the mid. We are so terrible. Okay.
Hold up. Terrible or funny?
I don't even know.
Don't even know this.
Don't even know.
Now we're gonna have to.
All right.
All right.
Now.
Yeah.
Oh, we don't have recursion, right?
If
Yeah.
it's equal, then we're just gonna return.
If right, if the key is equal to number sub mid, then we return mid, right?
Right. So now you can.
If we find it, return the index. Okay. Punch it. All right.
Magically.
Now. Now what?
Now we need to do.
If key is less than number sub mid,
If it's less than, then we need to return.
Playing with it. Keep it in
Which one's the?
so binary index, we're doing recursion. We're still passing in numbers, we're passing in key. So if key is less than mid, are we changing start?
We need to do 0.
No, we are changing end.
So it's start, we're still doing start, but now the end is going to be the mid.
Yes.
Wouldn't start be?
Because it's less than, right?
Yeah.
Right.
Wouldn't start still be 0?
In this example, yes, start would be 0. But we want a recursion in case we're trying to narrow it down.
Ow.
All right. So what about the other one? If key is,
The start would be mid and the end will be
now is it mid?
mid
Mid plus 1.
Plus 1.
And then the end.
End is still the same.
Okay.
Because we want to ignore the last element.
Right.
sure.
Right.
So we can actually get rid of this because all we're doing is just return binary index of numbers, key, 0, and size.
Whoa.
Boom.
Whoa.
Now,
Sure.
I'm going to look at this.
So what? I don't know. This is kind of confusing to me still. But which one comes first? Which function is like the one that you call first?
So this one, okay, good. Called first to set up recursion.
You spelled it right.
Thank you. The actual recursive
That doesn't look right.
That's not
binary.
actual.
So you call it, and it automatically then calls the recursive function.
Right. Well, it automatically it sets it up, right? Because it's setting it up where start is 0 and then end is size. Because this function's never passed those two.
Why, in the second function, why are we returning rather than just calling it again?
Wait, what?
In the function that comes second.
Yes.
Yeah, why, like, we're returning the function call. Why not just, like, call the function? I don't know. I thought that's how I
Oh,
remember
because
it.
binary returns an integer. If bad things happen, it's -1. If good things happen, we return mid.
Yeah, but then after that,
Then after that, we call ourselves.
Just want to do it again.
Call ourselves.
return the call.
Return. Well, binary index of returns something, right?
Yeah, so
Yeah, I guess so.
Basically,
So it's gonna call it and then come back eventually. Okay.
yeah, it'll
Gotcha.
go through each time, and then as it goes, it'll go back up with the numbers it came with. It was like that one picture you drew on the board.
The wife.
Oh.
Is he alright?
Aw.
She's okay. All right. Yeah, she's fine. Okay, does that make sense? I think y'all worked through it.
Yeah.
I listened to y'all do it. Okay, good. So this may not actually be correct. We're going to have a ton of off by one errors. Also, we should call the function.
Might be nice.
Slightly important.
All right, let's see if we get a good old infinite recursion. Oh, a segfault. Those are even better. That's good, because then... So we will gdb a.out, run it. Okay, cannot access memory, blah, 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 blah. Well, that's kind of weird. All right, linear search, line 40. 40?
Line 40? Turn
Oh,
the
wait.
numbers on.
Is that
Why don't you turn line numbers on?
Line number's on. Nah.
Yeah,
Alright.
you know,
54.
the things that tell you what number the line is.
I know what you're talking about. Start is 6-5. Okay, so what's happening here? Start is bouncing back and forth. It's instead of and end is not nothing's happening to end. Huh. I wonder if we broke it.
Wait,
You
why
did
is
not
start
break it.
6, 7?
So it's this is what's being called, but it's not being updated.
Why is
Oh, because our mid calculation is terribly, terribly wrong.
that was all you?
Fantastic.
Come on, guys.
Mid equals
Or is that not how you do it? How do you do it? Yeah, how do you calculate the mid?
Start plus.
Well, you just wrote it up on the board.
Yeah, we do.
Duh.
And divided by 2.
All right, so if you have 5 and 10,
Wouldn't it just be n divided by 2?
so then 10 minus, actually you could also do plus 5 divided by 2 would equal what?
yeah.
There, I drew a fancy 7.
Whoa.
Or the algebraic.
So we could just add it and then divide by 2.
Okay.
No? Well, isn't that what I just did on the board?
But don't you just divide the n by 2?
So you're getting controlled by the
Yeah.
computer now itself?
Didn't you just divide n by 2?
Well, if you
Not
did.
necessarily, because what if you're doing the
Oh,
top half?
because, well, if n is 2025 divided by 2 is what? That's an equal sign.
1012.
12.5. So we
Right, so then how would that be 7?
That'd be 7.
I'm confused.
So if start
Be 7.
start equals 5, end equals 10,
Yes.
we need to find the mid. So I do end plus start divided by 2 equals 7.
Okay.
Size might be 2025 divided by 2 is 1012, which is not 7.
Okay.
It will
I
never be
think-
7.
Well, if you use discrete math,
You can clearly prove.
2 plus 3 equals 6. Then 2 plus 7 equals 10.
All right, so we're back here.
Love it.
Let's see if we can do anything better this time.
Is 2 plus 2
Oh,
equal
hey, look at that.
No.
Oh, it works.
Oh,
If you
maybe.
draw it, yes.
Maybe.
Some searching.
Multiple tests.
All right, we're gonna throw out a lot of tests for this one, but I'm gonna make my life easier. Hope that's okay with everyone.
Oh, well? Oh, yeah, definitely.
I'm not even.
Segmentation fault.
Ah, if it's not found, sadness occurs. All right,
Sadness occurs.
I think I know what happened. Run.
What, we don't have a
Yeah.
case for if it's not found.
Right, because start is 8, end is 8. Ah, see, we didn't do the.
If start equals n.
Well, if start is greater than or equal to end, then return -1. If start equals end, and what was it? key sub start does not equal, I don't know why I wrote in the word key. Numbers sub start does not equal key, then you want to return -1.
Wouldn't you just?
Okay.
Wouldn't you do? Can you do that all
Base
in one
case,
line?
1 start is greater than end, and then base case 2 start equals end, but it is not the value we are looking for.
Why'd you do it in 2 different statements instead of combining it?
For clarity,
Okay.
I could combine it, but for clarity. Oh yeah, down there on the right. Otherwise, we recurse.
You misspelled that.
Otherwise,
Otherwise, still misspelled it.
You
If you
for a
missed those
VR.
letters, there you go.
I love this course. Recurse on lower half.
At least we're trying to keep it straight with it.
Recurse on upper half. All right, let's see if that helps any.
I don't like you.
There we go. Luckily, we also have all the values detached. Isn't that great? 6371. Come on, someone's got to play some music while I type all this in.
Play the dancing.
Great. Play Shake It Off. So you can dance like the turtle.
Yeah, go for it.
I was kidding.
If you're watching this, fast forward. It's gonna take. I just want to try all the numbers. Whoops, I missed one.
The name.
241240.
Well,
Wow, wow, wow.
Good, the bad, and the ugly.
My wife did not know where that came from, and I was like, "We're watching this movie," and every time it started, she couldn't stop laughing because they took it so seriously throughout the whole movie. But that sound, I guess, to her mind, she just thinks it's the funniest sound.
It's a good movie. It just gets long after the third one.
After the third one?
Name that movie.
Spider-Man.
Nice.
Oh, that.
dang.
All right, let's see if it works. Hey, look at that. So we're probably okay.
Probably.
Yeah, let's
I
go.
don't answer the probabilities now. I need a definitive. We're okay.
I don't like to leave things up.
Well,
We'll go
by the halting problem, there's no way I can definitively tell you we're okay.
Well, that's not.
I'm never
Yeah.
okay, so.
Because I thought I was having
All right, we'll go increase the size to something obnoxious like that. Oh my goodness! Bubble sort. Oh, bubble sort.
It's taking
It's
so
so
long.
long. Oh, bubble sort. Wow. Okay,
Huh. Okay.
let's remove a 0. See if that helps any.
That helps a lot.
Anyways,
Let's turn on optimizations.
I like the pixel, but it just needs improvements.
What is that?
Maybe next generation.
Okay, bubble sort is still terrible. There. Wow, bubble sort.
Hopefully nobody has that anymore.
Okay, so
Add those numbers.
and then we just double it, and bubble sort's going to take even longer. Oh my goodness, bubble sort.
Well,
See watch time,
manufactured.
and then if we decrease it by half, wow. Okay. All right.
What is that at the end?
Oh, that's how you do timings in Unix or Linux. You type in time space a.out and tells you how long your program took to execute.
Speaking
These
of-
numbers are not perfect. You need when you take timings in your lab, you need to do it the way I told you to, and during that one class. But yes, what's your question?
So, on the project, it says something about the memory size, returning the memory size. How do we do that?
You need to calculate how much memory you are taking up.
How?
Yeah.
Quick question about that. Okay, with an array, technically you
Yeah, I
cannot
heard they
free up the memory.
Correct.
You need the whole array. So when we return memory, do you want to just like return the amount of space we're taking up in the array?
No, you need to
Like-
return the entire memory size, the array size.
Okay.
How?
Okay, cool.
So if you have an,
What are you saying? Saying
all right.
here?
So let's say we have numbers, right?
Yeah.
And they're of what integers? All right. So I'm going to go down here. I'm going to go std cout. What?
So we're bringing back the STDs.
Size of numbers is. All right. So how many numbers do we have?
Lots.
Size times, and how many bytes are in an integer? Well, you can't.
8.
8.
4.
4.
1.
If you can't remember, you can type in size of int, and it'll just tell you.
Oh, that works.
4 bits.
Yeah.
Right? So 1
Bytes. 4 bytes.
4 bytes. Yeah, that's right.
Bytes of
See, when
six.
you don't respond quick enough, you make people question themselves.
I love making people question themselves.
That's
All right.
not nice.
He's a philosopher. Get used to it.
You should learn to be a skeptic of everything, including your own skepticism.
What?
Yeah.
That doesn't even make
Then
sense.
turn yourself off clip because you go crazy.
Skeptic about your skepticism.
That's
Right. Because, well, if you're a pure skeptic, then you're not going to accept anything,
Wait.
which is ridiculous.
Wait. So if you're a skeptic even of your own skepticism, wouldn't you fall off a cliff, as Shay would say, because you just don't know anything?
No.
You went through
You
yourself
you
off
know
clip.
stuff. You're
Skeptic just
skeptical
mean-
about it.
Yeah, you're just skeptical about it.
You don't
You're
know if it's
skeptical about
100%
whether or not
true,
you're a
but
skeptic.
Yes, you're skeptical. Well, you are skeptical if your own skepticism is actually merit or has merit. Because you can be skeptical of something, and then you can say, hey, look, we're not really, we shouldn't be skeptical of this because of blah, blah, blah. That's being skeptical of your own skepticism.
What book did you learn it from?
I feel like the definition
I have no
that
clue.
you're presenting here is a little
You cite your sources.
It's recursive skepticism.
It's recursive skepticism. I need to cite my sources.
Moving on. What's next?
Good talk. Good
So
talk.
we always have good talks.
So that would be how like we would do it for ours. You'd
Yes,
decide-
except one, yeah, that's.
But ours is an integer, so. it would
So
be
you need to find size of,
Size of
so if you have a class, you can do a size of that class and it'll tell you.
You can do that.
Yes.
Do you type the name of the class?
Yes,
in?
oh, I can't say that
Or you say
anymore.
Class.
So what?
Yes, we can. I can't say that anymore.
Why?
Sorry, I already paid it. Sorry.
We, the president, he changed over. Now, what am I supposed to say now?
Wait, what? You're actually not allowed to.
What?
I said wrong.
Wrong.
Fired! Or this is great! And it's going to be great. Everyone's going to love it.
No,
It'll be the
see,
best thing
honestly,
ever.
When you
I
said
don't even
that,
know.
like, it reminded me of like a kid's show, like Child the Builder.
Yeah.
Yeah.
What?
We did it.
Line.
Yes, we can.
Yes.
Make America sad again.
No, no. I don't even know what I can say.
Yes, we can.
I think I deserve at least.
Well,
a
no, no,
B
because
plus
then I was
for
just
being-
following our president at the time. Because that was a
Does it
slogan.
say that?
Yeah, that was his campaign slogan the whole time.
I have.
Yes.
I'll do a solid
I'm
7.
playing.
I have the two questions.
Ah.
Okay, so when, now we're going to the Bob builder. So when we're doing, instead of how we have size times size of, it would just be the size of the class.
Right.
Right?
But how do you write that? Do you write size of class, or do you write like size of and then the name of the class?
I think it's the name.
All right, you know what? Hang on.
Now we're getting off topic.
Hold on. Hold on. Are there any more questions about linear search, binary search, or bubble sort?
No.
Because if not, I want to stop right here so I can do another recording. That way, when you ask me later on, you can just skip to it.
I like that
Greatest
too.
ever.
That is the greatest. All right.